Okay, so let's then move on to quantum mechanics. So in quantum mechanics, we can have the analogous situation where, say, we have an atom. By the way, thank you very much for participating in this, in this survey. It is very nice to see that people they feel emboldened to express even when they're not sure. So again, learning physics is not about getting it right or wrong, but actually having the courage to think and and then re-examining where is it that you made a mistake, if you did make a mistake. Okay. All right. So for example, an atom consists of smaller particles which may have spin or orbital angular momentum, right? So, we want to know how, when we combine two systems, the combined system, what kind of angular momenta and spin the combined system can have. So before we examine the quantum mechanical counterpart of the problem of addition of angular momentum, let me briefly review for you the mathematics that is needed for combining quantum systems. Okay, so so suppose that we have a multipartite quantum system. Okay. And for the sake of argument here, we'll just take a bipartite. So let A and B be two quantum system. So quantal is the adjective of quantum. It's not often used, but it exists. So each of them have a Hilbert space, HA and HB. Now suppose you bring them together, then you want to describe them as one system. Then what is the mathematical structure that allows us to do that? So there should be a Hilbert space for the combined system, which I'm going to call HAB. And the assumption is that HAB is equal to the tensor product of HA and HB. Okay, this is the assumption that we make in quantum mechanics, and it's verified by experiments. So you may have seen tensor product either in your linear algebra course or in your tensor analysis course, but I'm going to give you a brief introduction to tensor product anyway. Okay. So what is tensor product? Suppose psi of A is a state in my Hilbert space A, and phi of B is a state in my Hilbert space HB. At the same time, we assume that EI of A, this forms an orthonormal basis for HA, okay, where I goes from 1 to the dimension of A. And at the same time, we assume that EA of B, where A goes from 1 to dB, forms a basis for HB. Okay? Is this clear?
Yes, sir.
So, if I know what the basis states are, I only have to specify what the coefficients are of this state when expressed in this basis, and then I have everything I want to know about this state, right? I just need to know the components, right? So, for example, if I'm working in three-dimensional real space and my basis vectors are I, j, k, I only have to give you the ax, ay, and az, and you know what the vector a is, right? So given some basis, we just have to specify the components of a vector. So we can express psi of a as, say, psi a I e I a. There is a sum over I. Okay. Similarly, we can express phi of b in terms of the basis where a goes from 1 to the dimension of b, and phi of b of a. Right? So these are the components or the projections. So all of this should be very clear to you conceptually. If not, just ask me. All right. So the question now is that what will be the tensor product of these two states? So suppose that I have one of the system, and it's in some state psi a, and another particle. So this is system A, another system which is in state phi b. Now, what is the combined state? Let's call the combined state chi, and it's AB, and it's given by the tensor product of psi A and phi B. Okay, so what is this tensor product? So before we, what we can do is that we can look at the tensor product of all the basis states. So if I take E, say E I of A, and take the tensor product with E A of B, then how many objects are here? I goes from 1 to dA, and A goes from 1 to dB. So the question is, how many objects are there?
dA times dB.
Right. So there are. So the dimension of, so this can act as the basis vectors for the tensor product of the Hilbert space, and then the dimension of the combined Hilbert space dA, dAB is dA times dB. Or this is just product, no tensor product. These are just numbers. So what is tensor product? I really haven't told you. It's a bit of a circular game I'm playing. And the idea is this. So now you know that chi of AB is, I'm defining it with psi of A, tensor product of phi of B. But now if I express it in terms of the components, the first guy is going to give me I goes from 1 to dA, psi IA. The second guy is going to give me phi. And again, there would be a sum over, say, let me move this over a little bit. So there are two sums. So this is a big sigma. And there's a sum from A to A from 1 to D, B. And this is A of B. And then the basis vectors here, which is going to be E of IA tensored with E of A, B. Okay, so so basically what we can say is that these things, so here I and A, I'm not going to bother with the limits again. So this guy is going to be the component of the chi AB vector in this chosen basis. So we know that, if you specify the components of a vector, we are, with respect to some orthonormal basis, we are specifying the whole vector. So what we have found is that if I take a tensor product of two states, then its components are given by simply the products of the components of the product states. Okay, so this is basically defines tensor product in terms of components. Tensor product is nothing but product component wise. Okay. It is the most
Is it a generalized version of the dot product in some way?
No, dot product is very different.
Sir, so what do we do with the basis EI dot cross, not the cross, tensor product EA, those two bases?
What do you mean?
Like chi AB, after that there's this expression, basis EI a tensor product, yeah, this one.
Yeah.
Like, what does this mean actually?
So these are basically basis vectors of HAB. Okay, and these are the components.
This is just a representation at this point.
Yeah. And what I'm saying is these components can be expressed in terms of this component and this component in this way. So tensor product is the component-wise product. This is not the most sophisticated definition. This is a definition that works for me. Okay, is the component-wise. As you can see, this is not a math class. That was a good laughter. This is the tensor product is the component-wise product of the of the what should I say, of the product vectors, or the smaller vectors, or of the vectors which go into the product. Okay, so let's do an example. Example is, say, the tensor product of a spin half particle. Say in a spin up, it's an electron, and a tensor and a product of a spin off particle, which is a proton. So this we know, we suppose we take, this to be our basis. In this basis, this vector is going to be, I'm just putting it in quotations because I'm meaning in this basis. This will be just this 1, 0, right? And in the same basis in the same kind of basis, so I'm just copying it over here. This is for the electron. And this is for the proton. For this same basis, the plus of the proton is this. Then what is, this tensor product? Well, component-wise, I just multiply this. 1 times 1 is 1, 0, 0, 0. So I multiply this with this, this with this, this with this, this with this. Okay, and you can show that. Okay, what are the bases? The basis was that this was the orthonormal. Well, this itself is a basis vector. This is a basis vector. This is a basis vector. This is a base. Sorry. This is a basis vector. This is a basis vector. And it's very easy to show that the first vector is 1, 0, 0, 0. The second vector is 0, 1, 0, 0. Third vector is 0, 0, 1, 0. And the fourth vector is 0, 0, 0, 1. Okay. And this, my dear friends, is a show. Okay, show it for yourself. Okay, any questions?
No, sir.
Okay. All right. So